Hi everyone and welcome back to the second module, EDR Internals in the Evasion Lab course by Altered Security. In this part we will take a look at the EDR Internals architecture and some components that generates EDR's telemetry. So starting by the architecture, this diagram illustrates the internal architecture of EDR, endpoint detection and response. It shows how the EDR collects telemetry data from various sources in both user mode and kernel mode, enabling comprehensive monitoring and threat detection. The EDR leverages multiple components including ETW, event trace for Windows, for system-wide telemetry, hook delays for monitoring API calls in user processes, network filters for capturing network activity, EDR driver for intercepting kernel callbacks to track processes, threads, registry of objects, and file system activities. So ETW, event trace for Windows. ETW is a powerful tracing mechanism in Windows that provides system-wide telemetry. ETW providers in the system generate events for critical activities such as process creation, image loading, network communication, memory allocation, and more. These events are written to ETW sessions, which EDR processes consume in real time. This enables the EDR to monitor system behavior at a low level, collecting high-fidelity telemetry without impacting performance. Attackers sometimes attempt to disable ETW providers to evade detection. Hook DLL. The hook DLL is injected into user mode processes to monitor API calls. It hooks sensitive APIs to intercept and log function calls made by the application. The hook DLL then sends the hooked API telemetry to the EDR processes for analysis. Attackers often try to bypass these hooks using techniques like direct syscalls or unhooking. Network filter. The network filter is implemented using the Windows filtering platform WFP. It monitors network traffic at the kernel level by interacting with the network stack. The network telemetry is sent to the EDR processes for network traffic analysis. Windows filtering platform can be used by attackers to block EDR traffic as well. EDR driver and kernel callbacks. The EDR driver operates in kernel mode where it has higher privileges and can intercept low-level events. It uses kernel callbacks to monitor critical system activities, including process callbacks registered using PS set create process notify routine X to track process creation and termination, thread callbacks using PS set create thread notify routine to capture thread creation and termination, image load callbacks using PS set load image notify routine to monitor DLL and driver loading, registry callbacks via CM register callbacks X to observe registry modifications, object callbacks monitoring kernel objects like opening handle to process or threads, file system callbacks using mini filter drivers to monitor file system operations such as file creation, deletion, or modification. These callbacks provide detailed telemetry for process telemetry like command line arguments, parent-child relationships and privileges, thread telemetry like thread context and scheduling information, image telemetry like DLL and drive loading events, registry telemetry like changes to sensitive registry keys, object telemetry like interactions with kernel objects, file system telemetry like file access, creation, and modification events. EDR processes. EDR processes are user mode components that aggregate and analyze telemetry collected by the other modules to detect different and abnormal behavior. Now let's take a look at kernel callbacks telemetry, starting by process creation kernel callbacks. So process creation kernel callbacks are low-level routines in the Windows kernel that are triggered whenever a process is created or terminated. They serve the purpose of notifying registered drivers about process creation events, allowing these drivers to collect telemetry and monitor process behavior. These callbacks are commonly used by endpoint detection and response (EDR) solutions to detect malicious process creation patterns, capture important metadata like command line, parent process, full file image path for the newly created process. This telemetry allows EDRs to be aware of process creation events in real time and respond accordingly. These callbacks are stored in kernel array called ps create process notify routine. Each entry in the array points to a registered callback routine. When a process is created or terminated, the kernel iterates through this array and invokes each registered callback, passing relevant information about the process event. Process creation kernel callbacks are triggered when a process creation request is made from user mode. This occurs via system calls such as int create user process or int create process X or other related process creation APIs. In Windows, drivers can register process creation kernel callbacks routines using the following kernel APIs: ps create process notify routine, ps create process notify routine X, and ps create process notify routine X2. In this example, we are using the DCMP open source driver to collect process creation events. The DCMP open source driver is configured to enumerate the callback routine stored in the int psp create process notify routine array inside the kernel. It provides detailed telemetry about each registered callback, including driver name, identifying which driver registered the callback, and the callback routine address, the memory address of the callback function. We can see process creation kernel callback routine registered by wdfilter.sys and mssecflt.sys, which represents the Windows Defender and MDE drivers respectively. This diagram illustrates the execution flow of a process creation event that triggers a kernel callback, leading to EDR telemetry collection. A parent.exe, a parent process with PID 1, 2, 3, 4, initiates the creation of a new process, malware.exe with PID 5, 6, 7, 8. The parent.exe calls the Win32 API create process as user W exported by kernel base. This API is commonly used to create a new process with the security context of another process. This API then calls the native API int create user process exported by int.dll. Thus prepares the necessary arguments for process creation. Then the syscall instruction is executed, causing a transition from user mode to kernel mode, passing control to the Windows kernel. Once in kernel mode, the syscall is handled by the Windows Process Manager, which allocates the eProcess structure for the new process malware.exe and creates the key process structure to manage its kernel state. It then calls an internal kernel function called psp process notify routines. This function iterates through the registered process creation callback stored in the psp create process notify routine array. This array holds pointers to all registered callbacks from drivers interested in process creation events. In this diagram, the array contains a couple of entries. These entries represent the callback routines represented by driver 1 and driver 2. These could be the system drivers or other loaded drivers, and EDR.sys. The EDR driver registered a callback to monitor process creation events. As the PSP call process notify routine function iterates through the array, it triggers the callback routine registered by the EDR process notify routine EDR at index 2. Following telemetry are collected and generated. Process ID and parent process ID of the newly created process malware.exe. The image file path, full path to the executable malware.exe, and its command line arguments used to launch the process. And extra information like security token information to identify privilege level and integrity. Then the collected telemetry is then sent to the EDR user mode process EDR.exe for further analysis or writing ETW session, or writing all those informations to ETW session. Then EDR.exe can consume it from that session. In user mode, the EDR process EDR.exe receives the telemetry data from either EDR.sys or from indirectly from ETW session. It then starts actively monitoring malware.exe, the newly created process, by scanning its memory, injecting a DLL to monitor APIs, or attach a remote debugger to monitor APIs as well. And it can analyze extra ETW events related to that process creation events. When a process creation kernel callback is triggered, it collects critical telemetry about the newly created process, such as e-process of the created process that includes a huge amount of information such as unique process ID, image file name, token, process, protection level, thread list head. It collects also the PID of the created process and the PPS create notify info, a kernel structure that contains parent process ID, image file name, which is the path to the executable that created the process, command line, the thread ID of the creating thread within the parent process. Now let's take a look at the thread creation kernel callbacks. Thread creation kernel callbacks are low-level routines in the Windows kernel that are triggered whenever a thread is created or terminated. They serve the purpose of notifying registered drivers about thread creation events, allowing these drivers to collect telemetry and monitor thread behavior. These callbacks are commonly used by endpoint detection and response EDR solutions to detect malicious thread creation techniques, capture critical metadata such as thread ID, start address where the thread executes, process ID, the process ID where the thread was created, and parent process ID, the process that created the thread. This telemetry allows EDRs to be aware of thread creation events in real time and respond accordingly. These callbacks are stored in a kernel array called PSP create thread notify routine inside the kernel. Each entry in the array points to a registered callback routine. When a thread is created or terminated, the kernel iterates through this array and invokes each registered callback, passing relevant information about the thread event. Thread creation kernel callbacks are triggered when a thread creation request is made from user mode. This occurs via system calls such as int-create thread X and int-terminate thread and much more related thread creation functions. In Windows, drivers can register thread creation callback routines using the following kernel APIs: psset create thread notify routine and psset create thread notify routine X. In this example, we are using DCMB open source driver to collect thread creation events. The DCMB open source driver is configured to enumerate the callback routines stored in the PSP create thread notify routine kernel array. It provides detailed telemetry about each registered callback, including driver name, identifying which driver registered the callback routine address, the memory address of the callback function. We can see thread creation kernel callback routines registered by wdfilter.sys, which is Windows Defender's kernel mod filter driver, and mssecflt.sys, Microsoft Defender for Endpoints MDE protection driver. This diagram illustrates the execution flow of a thread creation event that triggers a kernel callback leading to EDR telemetry collection. A process, malware.exe with PID 1234, initiates the creation of a new thread inside its memory. The thread creation flow follows these steps. The malware.exe calls the Win32 API create thread exported by kernel base, which is used to create a new thread inside a process. This API then calls the native API in inti.dll inti create thread x, which prepares the necessary arguments for thread creation, then calls the instruction and execute the instruction syscall that will do the transition from user mode to kernel mode. Once in kernel mode, the syscall is handled by the Windows Process Manager, which allocates the eThread structure for the new thread and links the thread to the eProcess structure of malware.exe. It then calls the kernel function PSP call thread notify routines, which iterates through the registered thread creation callback stored in the PSP create thread notify routine array. This PSP create thread notify routine array holds pointers to all registered thread creation kernel callbacks from different drivers interested in thread creation events. In this diagram, the array contains multiple entries representing the callback routines registered by driver 1 and driver 2. These could be any loaded drivers, maybe system drivers. And we have EDR.sys callback routine for EDR.sys, which monitors thread creation events called thread notify routine EDR. As the PSP call thread notify routines function iterates through this array, it will trigger the callback routine registered by the EDR driver thread notify routine EDR at index 2. This callback routine will collect the following telemetry: thread ID and process ID of the newly created thread, the thread start address, which this thread pointing to and executing, and the security token information for that thread. The collected telemetry is then sent to this EDR.sys and forwarded to EDR.exe, the user mode process, for further analysis, or reaching to ETW session that the EDR.exe is consuming from. It then starts actively monitoring this newly created thread by scanning the memory that it's pointing to, or injecting it DLL to this malware.exe process, or using remote debugging to monitor API, or using hooking to monitor API as well. It can also analyze extra ETW or use extra ETW events related to this thread creation event to detect any malicious behavior. Hi everyone, and welcome back to the second module, EDR Internals, in the Evasion Lab course by Altered Security. Let's continue with image load kernel callbacks. Image load kernel callbacks are low-level routines in the Windows kernel that are triggered whenever a PE image is loaded into memory. For example, .exe.dll.sys. They serve the purpose of notifying registered drivers about image loading events, allowing these drivers to collect telemetry and monitor image execution. These callbacks are commonly used by endpoint detection and response EDR solutions to detect malicious image loading techniques such as reflective DLL injection or on-sign driver loading, and capture critical metadata such as image name, process ID of the process loading the image, base address where the image is mapped in memory. This telemetry allows EDRs to be aware of image loading events in real time and respond accordingly. These callbacks are stored in a kernel array called psload image notify routine inside the kernel. Each entry in the array points to a registered callback routine. When an image is loaded, the kernel iterates through this array and evokes each registered callback, passing relevant information about the image load event. Image load kernel callbacks are triggered when a PE file is mapped into memory from user mode via system calls such as into map view of section or LDR load DLL. In Windows, drivers can register image load callback routines using the following kernel APIs: psset load image notify routine or psset load image notify routine X. In this example, we are using the DCMB open source driver to collect image load events. The DCMB open source driver is configured to enumerate the callback routines stored in the psload image notify routine array inside the kernel. It provides detailed information about each registered callback, including driver name, identifying which driver registered the callback, and callback routine address, the memory address of the callback function. We can see image load kernel callback routines registered by Windows Defender's kernel mode filter driver wdfilter.sys and Microsoft Defender for Endpoint MDE's driver mssecflg.sys. These callbacks allow security solutions like Windows Defender and MDE to monitor image load events in real time, helping to detect DLL injection, on-site driver loading, and malicious executable mapping. This diagram illustrates the execution flow of an image load event that triggers a kernel callback leading to EDR telemetry collection. Process malware.exe with PID 1234 initiates the loading of a new module malware.dll into its address space. The image loading flow follows these steps. Malware.exe calls the Win32 API load library A exported by kernel32, which is used to load a DLL into memory. This API then calls the native API EDR load DLL exported by intdll.dll, which calls another native API int map view of section exported by intdll.dll that will trigger the syscall instruction. The syscall instruction will cause the transition from user mode to kernel mode. Once in kernel mode, the syscall is handled by the Windows memory manager, which maps the image malware.dll into the process address space and verifies its signature and integrity. It then calls an internal kernel function, psp call image notify routines, which iterates through this array, psload image notify routine, an array that holds all registered image loading callbacks routines from different drivers interested in image loading events. In the diagram, the array contains multiple entries representing the callback routines registered by driver 1 and driver 2, could be any loaded drivers, maybe system drivers, and callback routine for EDR.sys called image notify routine EDR, which monitors image load events. as the PSP call image notify routines iterates through this array, it will trigger the callback routine registered by the EDR image notify routine.edr routine EDR as index 2. This callback routine collects the telemetries, process ID of the process loading the image, the image file path for malware.dll, and the base address, the memory location where the DLL is mapped. Then the collected telemetries are sent to EDR, to the driver itself, and forwarded to EDR.exe, the user mode process, or written to ETW session that this EDR.exe consuming from. Then this EDR process starts actively monitoring malware.exe and its newly loaded module malware.dll. By scanning the memory of malware, the loaded module malware.dll, and analyzing other extra ETW related to the loading module events. When an image load kernel callback is triggered, it collects critical telemetry about the loaded image, including full image name, PID of the process into which the image is loaded, base address and size of the loaded image. The collected telemetry allows security solutions to monitor image load events in real time and detect techniques like reflective DLL injection, untrusted driver loading, and process hollowing. Now let's take a look at registry operation kernel callbacks. Registry operation kernel callbacks are low-level routines in the Windows kernel that are triggered whenever a registry operation is performed, such as read, write, delete, or query. They serve the purpose of notifying registered drivers about registry modifications, allowing these drivers to monitor and collect telemetry on registry activities. These callbacks are commonly used by endpoint detection and response solutions to detect malicious registry modification used for persistence or for privilege escalation attempts. This telemetry allows EDRs to track registry changes in real time and respond accordingly. These callbacks are stored in a doubly linked list headed by callback list head inside the kernel. Each entry in the list points to a registered callback routine. When a registry operation occurs, the kernel iterates through these lists and invokes each registered callback, passing relevant information about the registry event. Registry operation kernel callbacks are triggered when a registry modification request is made from user mode via system calls such as int_open_key_x or int_set_value_key. In Windows, drivers can register registry operation callback routines using the following kernel APIs: cmregister callback or cmregister callback X. In this example, we are using the DCMP open source driver to collect registry operation events. The DCMP open source driver is configured to enumerate the callback routines stored in the callback list head linked list inside the kernel. It provides detailed telemetry about each registered callback, including driver name, identifying which driver registered the callback, and callback routine address, the memory address of the callback function. We can see registry operation kernel callback routines registered by Windows Defender kernel mod filter driver, wdfilter.sys, and MDE driver, mssecflt.sys. These callbacks allow security solutions like Windows Defender and MDE to monitor registry modifications in real time, helping to detect persistence techniques, privilege escalation attempts, and unauthorized registry access. This diagram illustrates the execution flow of a registry operation event that triggers a kernel callback leading to endpoint detection and response telemetry collection. A process malware.exe with PID 1234 initiates an operation to open or modify a registry key for potential persistence or maybe configuration changes. The registry operation flow follows these steps. Malware.exe calls the Win32 API reg open key xw exported by kernel base used to open a registry key. This API then calls the native API in intdll into open key x, which trigger the syscall instruction, causing a transition from user mode to kernel mode, passing control to Windows kernel. Once in kernel mode, the syscall is handled by the Windows Registry Manager, which locates the requested registry key and performs access control checks to verify if the process has permissions to modify the key. It then calls an internal kernel function called cmp callbacks x, which iterates through the registry operation callbacks stored in callback list head doubly linked list kernel doubly linked list. These lists holds pointers to all registered callbacks from drivers interested in registry events, including the one registered by EDR.sys, the EDR driver, which monitors registry modifications. As the cmp callbacks x function iterates through the list, it triggers the callback routine registered by the EDR driver, registry notify routine EDR. This callback routine collects the following telemetry: registry key, path, process ID of the process modifying the registry, which is malware.exe, and the type of operation, either open, write, delete. The collected telemetry is then sent to the EDR user mode edr.exe for further analysis or written to HEW session. In user mode, EDR process edr.exe receives the telemetry from edr.sys or indirectly from HEW session that it's consuming the events from. It then starts actively monitoring malware.exe and its registry changes by detecting suspicious modification to start up registry keys and analyzing extra HEW events related to registry operation. When a registry operation kernel callback is triggered, it collects critical telemetry about registry operation, including phone name of the registry key, PID of the process performing the registry operation, TID of the thread within the process performing the operation. The collected telemetry allows security solutions to monitor the registry operations in real time and detect techniques like registry-based persistence, privilege escalation, and malware configuration changes. Hi everyone, and welcome back to the second module, EDR Internals, in the Evasion Lab course by Altered Security. In today's part, we will take a look at object operation kernel callbacks. So, object operation kernel callbacks are low-level routines in the Windows kernel that are triggered whenever a process or thread handle is created, duplicated, or modified. They serve the purpose of notifying registered drivers about object-related operations, allowing these drivers to monitor and collect telemetry on suspicious handle access events. These callbacks are commonly used by endpoint detection and response EDR solutions to detect malicious handle operations such as LSS memory dumping for credential theft, or monitor remote thread creation used for process injection and remote code execution. This telemetry allows EDRs to track handle manipulations in real time and respond accordingly. These callbacks are stored in a doubly linked list headed by PS process type callback list or PS thread type callback list. Each entry in the list points to a registered callback routine. When a process or thread handle operation occurs, the kernel iterates through these lists and invokes each registered callback, passing relevant information about the handle event. Object operation kernel callbacks are triggered when a handle request is made from user mode via system calls like int open process for opening a handle to process or int open thread for opening a handle to thread. In Windows, drivers can register object operation callback routines using the kernel API OB register callbacks. These callbacks allow monitoring and restricting access to process and thread objects, helping detect unauthorized handle manipulations. In this example, we are using DCMB open source driver to enumerate object operation callbacks. The DCMB driver provides detailed telemetry about each registered callback, including the driver name, identifies which driver registered the callback, and the callback routine address, the memory address of the registered callback function. We can see object operation kernel callback routines registered by mssec.sys, mssecflt.sys, which is Microsoft Defender for Endpoints MDE, which protects sensitive processes such as LSS by restricting handle access. This diagram illustrates the execution flow of an object operation event that triggers a kernel callback leading to EDR telemetry collection. A process malware.exe with PID 1234 attempts to open a handle to another process LSS.exe, which is commonly associated with credential theft techniques. Malware.exe calls open process a Win32 API exported by kernel base, which is used to obtain a handle to another process. This API then calls a native API in IntDLL into open process, a system call that prepares the necessary arguments for opening the process handle. The syscall instruction then is executed, transitioning from execution from user mode to kernel mode. Once in kernel mode, the request is processed and the kernel calls OBP called pre-operation callbacks, a kernel function that iterates through the registered object operation callbacks stored in PS process type callback list. This doubly linked list contains flick pointing to the next entry and plick pointing to the previous entry, and a pointer and extra data plus a pointer to all pre-operation and post-operation registered callback from security drivers monitoring process handle access. The kernel invokes those pre-operation and post-operation callback routines in the doubly linked list. EDR driver EDR.sys has registered pre-operation and post-operation callbacks via a kernel function called OB register callbacks function, allowing it to monitor attempts to access protected processes like LSS or restrict handle access if necessary to prevent credential dumping attacks. The EDR driver.sys using the operation call the kernel callback of objects pre-notify routine EDR will collect telemetry including target process, the LSS.exe, the requesting process malware.exe, and requested access rights, either process VM read for memory reading and dumping. The collected telemetry is sent then to from edr.sys to edr.exe EDR user mode process. We start actively monitoring malware.exe for further analysis. When an object operation kernel callback is triggered, it collects critical telemetry about handle creation or duplication events, including the target and source PID, identifies the process requesting access and target process. The desired access right requested specifies what level of access the source process is requesting, either read, write, or terminate. And the TID of the initiation thread captures the thread ID responsible for requesting the handle operation. And additional metadata can include access flags that help in detecting suspicious process handle manipulation. The collected telemetry allows security solutions and EDRs to detect malicious activities and actions like SaaS handle access for credential dumping attempts or process injection, open handle with the process create thread, and process VM write to the target's memory, and executing the remote thread, thread that will execute the shell code or whatever. Now let's take a look at file system operation kernel callbacks. Mini-filter kernel callbacks are low-level routines in the Windows kernel that are triggered whenever a file system operation occurs, like create, write, delete, or close on a file. These callbacks notify registered drivers about file system events, allowing them to monitor file operations and detect potential security threats. EDR solutions commonly use these callbacks to detect malicious file system operations such as dropping mimikatz or other hacking tools, ransomware, encrypting multiple files, or unauthorized modification to file system. These callbacks are stored in a structure called the callback node, which is used by mini filters to track registered callback routines. Drivers can register file system operation callbacks during mini filter registering using FLT register filter API. The callbacks are executed before or after file system operation. A pre-operation callback triggered before the file system operation occurs, and post-operation callback triggered after the file system operation is completed. So mini filter drivers such as EDR filters use layered architecture to intercept and monitor file system operations. Each mini filter driver or filter can have multiple instances, allowing it to hook into different file system volumes or operations. Within each instance, multiple callback node structures are registered for specific file system operations. A callback node is responsible for handling a specific file system operations, either create, read, write, delete, and so on. Each callback node contains pre-operation and post-operation kernel callback. The pre-operation callback at offset 18 and post-operation callback at offset 20, as we can see here in the callback node structure. We can see that this pre-operation callback is invoked before the file system operation executes. In this case, the pre-operation kernel callback for the MDE driver filter called the sec pre-create, and the post-operation kernel callback for that is invoked after the file operation completes for the MDE filter called sec post create. So when a filter kernel callback is triggered, it collects critical telemetry about file system. This telemetry helps EDRs tools to detect suspicious files access, modification, or encryption. The collected telemetry includes type of the file system operation, whether the operation is read, write, create, delete, rename. This helps track malicious activities such as unauthorized modification or ransomware encryption. The PID and GID of the operation performer, and the path and size of the affected file. This helps detect malicious file modifications such as ransomware encryption, as I said, credential dumping, persistence mechanisms, and more. Hi everyone, and welcome back to the second module, EDR Internals in the Evasion Lab course by Altered Security. In today's part, we will take a look at some EDR telemetry collection, starting by ETW telemetry and an overview on ETW architecture. This diagram represents the event tracing for Windows ETW architecture, illustrating how events are generated, stored, and consumed. The controller is responsible for managing ETW sessions, starting or stop ETW sessions to begin or terminate event collection, or enabling or disabling ETW providers to control which event sources are actively generating events. Providers are event sources that generate telemetry data based on system or application activity. It can be kernel providers or user mode providers. Kernel providers that track process creation, thread activity, file system operation, registry changes, and etc. And user mode providers can monitor application-specific activities. Providers write events into ETW sessions. Events are stored either in memory buffers or directly into ETL, event trace log file on disk. ETW sessions are responsible for collecting and managing event data. Each session maintains multiple buffers which temporarily store event data before it's processed. There can be multiple independent ETW sessions running simultaneously, each collecting events from different providers. Events generated by providers are stored in session buffers in memory, depending on configuration. Real-time events remain in session buffers until consumed, or logged events are written into ETL, event trace log file on disk for later analysis. Consumers are applications or tools that process events. There is two ways to consume events: either real-time consumers like consumer 1 that read events directly from ETW session buffers as they are generated, and there is logged event consumers like consumer 2 that read events from ETL files stored on disk. Now, this screenshot provides insight into Windows Defender's ETW, event tracing for Windows internals. Specifically, how MSMPENG, Windows Defender's core process, consumes ETW events. The WinDBG output shows that MSMPENG.exe acts as an ETW consumer, collecting telemetry from various sources. Two ETW login sessions are highlighted: Defender Audit Logger Session 1 and Defender API Logger Session 2. These sessions are responsible for capturing security-relevant telemetry and writing them to ETW log files located under C Windows System 32 log files WMI RT backup. Specifically, ETW RT Defender Audit Logger.etl and ETW RT Defender API Logger.etl. The first session, Defender API Logger, does not have any provider GUID registered, The second session, Defender API Logger, is linked to several ETW providers. These providers include Microsoft Windows Kernel General, Microsoft Windows Event Log, Microsoft Windows Storage Intelligence, and Microsoft Windows WMI Activity, among others. Each of these providers generates telemetry relevant to security monitoring, system events, network activity, and API interactions. Defender collects these logs in real time to analyze potential malicious behaviors, detect suspicious activities, and enhance its threat detection capabilities. By monitoring these ETW sessions, security researchers can better understand how Defender leverages ETW telemetry to detect threats, and attackers may attempt to evade detections by disabling or modifying these logging mechanisms by disabling providers or stopping sessions. Each ETW provider creates multiple events, each with a unique ID that serves a specific purpose. Some events have different versions, which add more details while keeping older information. Every event has properties that store useful data, and each property has a specific type like numbers, pointers, or timestamps. Now let's take a look at network telemetry. The Windows filtering platform WFP is a system used to control and filter network traffic. It's built on layers, which represent logical points in the network stack. Each layer has a pair, one for IPv4 and one for IPv6, and contains fields, properties that store network data. A filter can be applied to a single layer, and its action is triggered based on certain conditions. These conditions check the properties of the request and decide whether to allow, block, or modify the traffic. Applications interact with WFP using WFP APIs to filter network data. Endpoint detection and response EDR solutions use WFP to monitor network traffic and collect network telemetry. By applying filters and callouts, EDRs can inspect packets, track connections, and detect suspicious activity, such as command and control, C2 communication, data exfiltration, or malware traffic. Additionally, callouts are optional kernel callbacks that extend the functionality of filters, providing extra control over how network requests are handled. In the diagram, multiple filters operate within the filter engine, applying conditions and invoking callouts to take actions on network traffic. This diagram illustrates how an endpoint detection and response EDR solution monitors process creation and injects its DLL to perform API hooking for deeper monitoring. The flow starts with a parent process, parent.exe with PID 1, 2, 3, 4, which creates a new process, malware.exe. The process creation follows this step. Parent.exe calls the Win32 API, create process A user W exported by kernel base, which is responsible for creating a new process. This API invokes the native API int create user process exported by int DLL, which ultimately makes a system call, syscall, transition execution from user mode to kernel mode. The Windows kernel process these requests and call PSP call process notify routines, which iterates through registered process creation callbacks stored in PSP create process notify routine array. This array contains multiple registered callbacks from different drivers, which including EDR.sys, which is the driver used by the EDR solution. Once the EDR driver's callback is triggered, this process notify routine EDR, it collects telemetry related to malware.exe, the newly created process, such as its process ID, the parent PID, the image patch, and the command line arguments. The collected data is then sent to EDR from EDR sys to EDR user mode process EDR.exe, which further analysis the newly created process. At this point, the EDR.exe injects a DLL, EDR.dll into malware.exe to hook critical APIs. This screenshot shows a real case of DLL injection by Sentinel, where in process client 64.dll is injected into a running notepad process. In the clean create thread X, the function follows the standard syscall stub behavior. The instructions move R10, RCX moves the first argument RCX into R10, which is required for syscall conversion in Windows. Move EX C1 loads the syscall number C1 into EX, identifying the system service being called. Syscall triggers the transition from user mode to kernel mode to execute the corresponding system call. This is the expected unmodified flow of a native Windows API. In the hooked create thread X, however, this normal flow is altered by an inline hook instead of executing the standard syscall sequence. The function begins with jump to an address, a jump to an external memory location, typically an EDR or secure software's trampoline. This means the function execution is being redirected to an external monitoring module before the actual system call happens. The EDR hooking flow demonstrates how an endpoint detection and response EDR solution intercepts system calls like create thread X. The original system call stub in dll.dll is modified to redirect execution to an EDR control function. Instead of executing the normal syscall sequence move R10, RCX, move EX, C1 syscall, a jump instruction is placed pointing to the EDR's trampoline. The trampoline acts as an intermediate handler before the actual system call. It performs an additional jump to another function, EDR.dll create thread X hook, which is responsible for security checks. The hook function executes a set of instructions to inspect and log register values. After performing its analysis, the hook function jumps back to EDR.dll trampoline plus 0x5, skipping the initial hook instructions and restoring execution flow. Finally, it executes the system call properly via syscall, allowing normal execution if no threats are detected. Now, EDR uses several key mechanisms to detect and respond to threat effectively. AI and machine learning based detection helps identifying anomalies and suspicious behavior by analyzing patterns and historical data. Cloud submission and scanning allows files to be uploaded to cloud-based threat intelligence system for deep analysis. YARA rules and signature scanning enable detection of known malware based on specific patterns in files or memory. Threat hunting automation continuously scans for indicator of compromise to detect threats proactively. Sandboxing executes suspicious files in an isolated environment to observe behavior safely. Deception technology uses decoy credentials, fake files, or honey tokens to mislead attackers and detect intrusions. Finally, exploit mitigation includes techniques like stack integrity checks and memory protection to prevent vulnerabilities from being exploited.